Well, good morning or afternoon, students. This is Mrs. Gordon-Coy. I am here today, but we have several students who are out absent, so I thought we would go ahead and record what it is we're doing in class today so that you can properly study for your test on Friday. So yesterday, you had a lecture over what the different types of potential energy are. What we're going to do today is look at different examples of those and really work at getting a good understanding of what's the difference between gravitational potential energy and elastic potential energy. Actually, the question of today was, I'm looking at the board. Let's see here. There we go. Take it over to the board. It is, how are gravitational potential energy and elastic potential energy similar, and how are they different? So I must ask you to pay attention, and hopefully we'll be able to shed some light on what's going on with potential energy. So we're going to go ahead and oops, not that, don't need that. There we go. So looking at energy, realizing the potential. Again, Mrs. Gordon-Coy from Sandy Valley Middle School. So we talked yesterday about the different types of gravitational, elastic, chemical, electrical, magnetic, all those different types of potential energy. So why don't we look at each one of those close up. Gravitational potential energy, like we said yesterday, this is in the note packet that you received, deals with the position of the object, the mass of the object, and the gravity that that object is experiencing. So here we have a man on a bike, and he is going to be, he's going to be going down this hill. But we're going to go ahead and take him back up here. And we're looking at, I'm going to go ahead at the end. I don't know if I can move that or not, so we'll just leave that there. We're going to look at his potential energy based off of his mass, his height, and his gravity. Now, please remember, as we said yesterday, mass needs to be in kilograms, height needs to be in meters, and gravity is meters per second squared. So this young fella here is 100 kilograms. This height, now when we're talking about the height of the hill, we're talking about the position he's in all the way down here. So I'm going to go ahead, come over here, and use my marker. And I'm talking about if this was sea level, for instance, I am looking at this area right there as my 15 meters. Sorry, my penmanship not so good. There we go. 15 meters, and then gravity on the earth. So what we're going to do is we're going to go ahead and take 100 on our calculator, multiply that by 15, and then multiply that by 9.81, that's our gravity, equals 14,715. So we're going to go ahead and type that in there, 14,715, and that is joules. Joules is the unit for energy. Now, mechanical energy-wise, as this potential energy is converted, as he goes down the hill and it's converted to kinetic energy, remember kinetic energy is the energy of motion, that mechanical energy is going to be preserved. Mechanical energy is never really destroyed, it's just transferred. So potential energy transfers into kinetic energy, and of course there's going to be some friction with that as well. But potential energy due to gravity is completely based off of the man and his height. Now, if we would take the man and we would put him up here, what would happen? Well, his potential energy would go up. His potential energy would go up because his height went up. He didn't gain any mass, and he hasn't, gained or lost any gravity. But because he gained height there, his potential energy would go down. And started it there, he'd have less potential energy there. Potential energy due to gravity. Okay, the next type of potential energy we're going to talk about is elastic potential energy. Yesterday, you got in your notes that elastic potential energy is associated with how much an elastic object has been stretched or compressed. So let's look at some examples of those elastic objects. So we have slingshots, bungee cords. I'm going to say these are those little stretch things that you can use if you are in the gym. This looks like your standard rubber band. This is a spring scale. This is maybe Robin Hood, not really sure, but you can see he's got his bow and arrow. And then here we have our gymnast on a springboard. Woo, got very springy there. Okay, so she jumps on the springboard and she can go in the air. Maybe she does like a flip or something. I don't know. But when she's jumping on the springboard, she's compressing it. That gives it a great deal of potential, and then it flings her forward. Okay, so maybe she's flying into the air. Woo! Okay, so that is elastic potential energy. And so when you're looking at a rubber band, and I was going to have a rubber band ready to go, and of course I don't. I think you guys must have commandeered all of my rubber bands. I was going to stretch it out for you, but you can imagine if I stretched out this rubber band, I would be having a great deal of elastic potential energy. And as I released the object that I was flicking, or as I wrapped it around the papers or whatever I was using it for, then my elastic potential energy would be changing. Okay, chemical potential energy is basically another way of saying chemical reactions is what we're looking at. Is the potential energy associated with the position and arrangement of the atoms. So I have a couple things here we're going to look at. Here we have reactions of metals with an acid. So this is for all those people who want me to put sodium in things. Okay, it's not happening in real life, but here is a virtual sodium in hydrochloric acid. Now you put sodium in water and you have a hot mess. Well, here they have it in hydrochloric acid and oh, it broke. In reality, this experiment should not be attempted without the supervision of your teacher. I would go as far to say in the middle school and high school setting, you really shouldn't be doing it at all. It's not worth your eyeball. Okay, so let's reset. And we'll take magnesium. Magnesium's kind of fun. This is a little piece of magnesium ribbon. I'm going to put it in the hydrochloric acid. Okay, now it made a little hydrogen gas, so I'm going to take my match over here, and it makes a little popping sound. And quite literally, that's pretty close to what it sounds like when we actually do it. And if we have enough time, which is the plan at the end of the year, we'll try some of these things. All right, let's reset that and take a little zinc. Zinc's kind of fun too. And it says, oh, hydrogen. So if the hydrogen last time when we took the match to it made a popping sound, what do you think is going to happen this time? Well, we take the match and we put it over there. It pops again. It makes a little popping sound. So a match is a nice way when small amounts of hydrogen are created as a byproduct to indicate that that chemical reaction happened. Now, the zinc and the hydrochloric acid before I put it in there have a lot of chemical potential energy. Okay, so it's that idea of what could happen. Now, a lot of times with chemical potential energy, our byproduct is heat. All right, electrical potential energy. I went yesterday with the example of static charge, but I want to talk about electrical potential as it's associated with the actual flow. And it says charge moving through the wires of the circuit will encounter changes in the electric potential energy as it traverses through the circuit. So we're going to make a circuit here. Here I've got a battery and got a little measuring device, some sort of an amp meter, and my little switch. Now, technically speaking, I don't think I should have to add the switch. I think it should just be flowing. But for this particular app, we have to flip the switch. Okay, we flip the switch and we can see, and it measures in amps. There's 1 amp going through here, and then you're basically seeing the change in that potential. So once the potential starts to flow, then you get a measurable amount of electricity. So I'm going to put, well, here, let's just put 1 light bulb. 1 light bulb gives us 1 amp. So what's going to happen when we put that second light bulb in there? Now, next year's standards get into electricity, or if this is my advanced class, you guys will get into electricity here shortly. Okay, so that's the physical science component. But when we flip that switch, check out those amps. Oh, it goes down to 0.5. So if I wish I had a third bulb, you know, but if I had a third bulb, it would cut it into a third. So it'd be like 0.33, 0.33, and 0.33. But we will get into more about parallel circuits and series circuits and what the difference is between the amps on that. But this is just an example of the electrical potential actually then traveling through and creating the complete circuit, and light bulbs are lighting and life is great. Okay, magnetic potential energy, a little different here. Magnetic potential energy, it's associated with the position of the magnetic objects. I took that directly out of the standards. And one of the things I don't like about that is it does not go into the fact that you should realize if it's closer or further away, what that has to do with potential energy of the magnetism. And I think that's very ambiguous. So let's look into that a little bit. Oh, first, real quick, remember when I thought the aluminum had magically become magnetic because of the magnet that was underneath of it? Look, magnets are not attracted to the aluminum because it's not a ferromagnetic object. So let's reset that. We're not going to do the whole thing here, but if you have a little iron sphere, you could see my little magnet that pops up over here. You know, we could encourage that marble to go through the maze. Oops, it's kind of like me driving there. There we go. That's kind of funny. All right, so you can get the gist. Okay, we're going to go ahead past that. I thought this was fun too. These are refrigerator magnets, and I made the word magnetism out of refrigerator magnets. So I thought you might enjoy that. But when it gets into what's going on with magnetic potential energy, this was a question I found on the University of Illinois website. And I will tell you, if students at the university level are asking about magnetic potential energy, it is perfectly, completely fine for 8th graders to be a little bit confused about it. It says the law of conservation of energy says energy can't be created or destroyed. Okay, you've got that. So what's the deal? Remember, this is a student's question. What's the deal with permanent magnets? They spend energy attracting ferrous materials. Where does that energy come from? I'd like the answer. It says, why do you say that magnets spend energy? Let's get to this point here. If the material is attracted to the magnet and moves closer to it, the magnetic potential energy goes down. So this comes from a professor, not from me. My understanding of magnetism basically is if you're within that field and your object is attracted to it, but it's not as, I mean, it's basically as far as it can be, still having that attraction, it's going to have that potential energy. If the object is somehow stopped, the energy turns into thermal energy because it's going to keep trying to get to that magnet. But when we go back to the state standard, it says, let me go back a little bit, it says that you should understand that magnetic potential energy is associated with the position of the magnetic object relative to each other. Keep in mind that we're saying that the further they are from each other within reason, the potential energy will go up. The closer it gets to it, the potential energy goes down. Okay. I want to reiterate some of those misconceptions that an object at rest has no energy. That's absolutely not true. I talked to you yesterday about that. Potential energy, an object is sitting there at rest on a table, it definitely has potential energy. The only type of potential energy is gravitational. That's probably what you walked into this classroom thinking, but understanding that there are those other types, electrical, magnetic, elastic, there's so much going on with potential energy. Chemical, let's not forget chemical. That gravitational potential energy depends, there's a typo there, depends only on the height of an object. Well, we looked at that experiment with the man on the bicycle, and yes, it definitely does depend on his height, but it also depends upon the gravity and his mass. That the term energy and force are interchangeable. Just to keep you on your toes on that one, there was another question from that same student from the University of Illinois asking about that. So the fact that maybe you think that does not mean that you are alone in this world. It means that a lot of people think that energy and force are interchangeable. So I'm just here to tell you that they're not. And then finally, that energy is a thing or an object or something that's tangible. And although you can feel the force of the magnets, you are not touching the energy. All right, so we want to finish reviewing the packet. And so if you could turn your packets to page 18, we're going to talk about describing 3 properties of magnets. Oh, before I do that though, hang on, I'm going to minimize this. I had this I wanted to show you. I thought this was neat. Here is a bar magnet, and we can see the field lines. We can see the domains, and we can play around with it. Notice how they change. Remember we talked about magnetism is when those domains are lined up. And if they're a hot mess, if they're pointed in all different directions, you're not going to see magnetism. Now, if I click on here, show inside the magnet is kind of a neat thing. Look at that. You can see how they're flowing. Remember we said that, oh, look at that. I love that. Okay. Well, anyways, remember that we said that it's going to flow north to south. And we also said that the north end of the compass, or the compass part that's pointing to the north, really should just be saying that it's the opposite of that. So the north is really south seeking, or I'm sorry, north seeking. What we call north and what we call south is so arbitrary. So let's put the earth on there. Woo, there's the earth. Oh, and apparently, nope, the earth is not upside down. Notice this. Notice that we have the South Pole up at the north and the North Pole down at the south. Why is that? Well, because South Pole, okay, the South Pole of a magnet is really just another way of saying north seeking. It's so confusing sometimes to people. But just understanding that like attracts like, and that like opposes like, my mistake, and that opposites do attract. Here's an electromagnet. That's pretty slick. It's kind of like what we had going on in class where we had the battery, and we can change alternating current. That's kind of slick. But we're not going to get into the whole Tesla and Thomas Edison debate right now. All right, back to your packet. So I think if I can bring my Hangout up here. Whoa. Okay, I'm going to stop sharing. And it should come back. Here I am. Whew. Okay, so I am looking at the packet, and it says to describe 3 properties of magnets. So you want to make sure you have your packet out. Describing 3 properties of magnets. Okay, magnets are objects that are made out of iron. But we also said that they could be nickel, and we looked at neodymium. So there's different, and cobalt too, if I remember right. So there's different materials they can be made of, but they need to be made out of a magnetic material. Also, magnets have 2 poles, north and south, and magnets are surrounded by a magnetic field. Number 18, list 2 ways in which the strength of an electromagnet can be increased. We can either increase the number of loops, the copper loops, or whatever conductor you're using. We can also increase the electric current running through the wire. So those are 2 ways that you can do that. All right, on the back page, we have this image of the Earth. Okay, is everybody there? Very good. And it says the image below shows Earth and its magnetic field. We have north magnetic pole and then north geographic pole. So what they're basically saying is, hey, all right, here is right here the geographic north pole. Guess what? That's not going to change. Oh, the bell just rang. So I'm going to have to stop the broadcast because you're going to be here soon. And if you're someone who's absent that I was making this for, please make sure that you finish the packet so you're ready to go for tomorrow. All right, thanks and have a great day.